Hello everyone, welcome to my presentation. My topic today is about Advance Virtual Channel Reservation. I would like to show my presentation in 6 parts. Firstly, I will give the motivation and then explain the concept of AVCR. In the third and first part, I will show the process of AVCR in details, including the basic and optimized mechanism. An application example will be given in the 5th part. And finally, I will conclude in the 6th part. Firstly, motivation. In a virtual channel-based network-on-chip system, package will occur delay caused by VC allocation and the switch arbitration. Especially for those memory-intensive applications, the heavy traffic will result in tremendous package delay. Previous work usually focused on the router microarchitecture, like short pipeline, fast allocation to reduce package delay. Instead, we find that we can predict or know the destination of some request-response package ahead before they arrive at the network interface, which offers the opportunities to reduce the package transfer delay. Taking the CMP architecture with the private L1 cache, shared L2 cache, and off-chip memory as an example, as shown in Figure A, if the L2 cache receives a request from the L1 cache, we can predict a response back to the L1 cache, which usually happens to a great extent. If the prediction is wrong, the request will trigger the forward request to the remote L1 cache or off-chip memory. For the request to the remote L1 cache, which is shown in the Figure B, we can definitely know that there will be a response from the remote L1 cache to the local L1 cache. For the request to the off-chip memory, which is shown in Figure C, there will be a response from the memory to the L2 cache and then to the local L1 cache. Therefore, we can predict or know the destination ahead in many cases, and based on this, we put forward a service named AVCR. Then the concept of AVCR. It is a package acceleration scheme designed to accelerate target package in NOx. It is realized by applying VC reservation combined with arbitration priority, and it is based on the possibility to know the package destination ahead, as we explained before. We proposed AVCR both for the request and the response package. Here, I firstly show the response process. As shown in the figure, conventionally, the package has VC allocation and switch arbitration delay apart from the network transfer latency after the response package is ready in the NI. While in AVCR, once knowing the destination, a reservation head fleet will be sent out to establish the highway by reserving the VC resources and being allocated a higher arbitration priority. In this way, the head fleet will occur allocation and arbitration delay instead of the target package. And when the target response package is ready in the NI, it will enjoy the highway, decreasing the transfer delay. In the request process, which serves the repeated request between a source-destination pair, in this scenario, the highway will be established by the first request. Then the following request to the same destination can enjoy the highway to decrease transfer delay. Now let's look into the detailed process of response AVCR. When the request package arrives at the network interface, a reservation head fleet with control information will be generated by the AVCR controller and sent to the predicted or known destination to establish the highway. The AVCR controller in each router is responsible for recording the reserved buffer and offering the highest priority to the reserved buffer. When the response package is ready, it uses the highway and its tail fleet will finally release the highway. The VC reservation and release process is based on the basic virtual channel flow control mechanism, which will not cost additional overhead. For the details of a request AVCR process, the first request will be sent out as head and body fleets to reserve the highway. The sequential request package will all be sent out to the highway as body fleets, with a special target to identify its end. Finally, a time counter is designed to generate and send out a cancel fleet to release the highway after timeout. This unit is also utilized in the case where the destination prediction of response package is wrong. Then we would like to show three optimization methods to improve our proposed basic mechanism. One drawback of the basic mechanism is that it will waste buffer resources if a long-time reservation is made without usage. So we proposed a way to predict the best point to send out the reservation head fleet. The establishment of the highway and the transfer of the target package could happen at the same time. The best case is that the first fleet of the target package can arrive at the destination just one cycle after the reservation head fleet without any conflict during the transfer. Based on this case, we proposed the equation to calculate the best sending point. If the result is not bigger than 0, send the reservation head fleet immediately. Otherwise, send it T cycles later. Besides, in our design, we only use one VC per port to support advanced reservation, which means that the head fleet for reservation could be blocked by each other, influencing the performance. To solve this problem, we proposed a highway combination mechanism, as shown in the figure. If two highways from different sources have the same target, they can share the same highway path from the joint router. The details in the router 2 are shown in the right figure. They will only reserve one VC in the downstream routers, which assure that one reserved VC per port. The NIID is tagged to each fleet for distinction. It can increase resources utilization and decrease the influence on the other packets. The third optimization is applied to the highway from the memory to the L2 cache and then to the local L1 cache. Sometimes, the access time interval in the L2 cache is too short to benefit from the pre-establishment of highway. In this case, the response package could possibly catch up the reservation head fleet before they arrive at the destination, influence the latency decrease. This mechanism is proposed to solve this problem. It combines the establishment of highways from the off-chip memory to the L2 cache and the highway from the L2 cache to the L1 cache together through bypassing the reservation head fleet. So the response package from the L2 cache can also enjoy a shorter transfer time. We tested the performance of our proposed mechanism by applying it in two cases. We applied the response AVCR mechanism to the package generated by the slowest threads and the request AVCR mechanism to packages generated for the lock request process. We conduct experiment in Gen5 for system simulator with noise cache coherence protocol. In our design, the network is in an 8x8 mesh NOC architecture. with one node connected to one router. By applying response AVCR to the slowest threads, that is threads 0, 2, 8, 10 in this case, we can see that the thread balance has been greatly improved, and thus the application execution time can be decreased. Here, we compare the parallel phase execution time with the result produced by the OCLR MPG, which is also focused on the acceleration of lock request phase and the priority mechanism. We can find that AVCR mechanism can have the best result in most cases. Finally, let's make conclusion. AVCR is based on the possibility of knowing destination ahead. By making full use of this possibility, we can decrease packages with allocation and switch arbitration delay. Besides, we also propose some optimization methods to enhance resource utilization. Finally, by applying AVCR to the slowest threads and the lock request phase, application's performance can be greatly improved. So that's all. Thank you for your attention.